Good afternoon, everyone. So today we will move to a new topic, that is bar magnet as an equivalent solenoid. We have studied bar magnet and the field lines around a bar magnet. So the magnetic field lines for a bar magnet and a current carrying solenoid resemble very closely. You have seen that. And if you are cutting a bar magnet in half, it is like cutting a solenoid, and we get two smaller solenoids with weaker magnetic properties. The field lines will remain continuous, emerging from one phase of solenoid and entering into the other phase. Okay, so here we can prove mathematically that the magnetic field produced by a solenoid on any point on the axial line is same as that of the bar magnet. That means if you are considering a solenoid like this, okay, so this is the axial line of the solenoid. Now at any one point, if you are considering here and you want to find the magnetic field at this point, you will get an expression. And when you check, you can confirm that the expression that you are getting at this point for the solenoid will be same as that of the expression for magnetic field in the case of axial line of a bar magnet. Okay, and let me say one thing, in your revised syllabus, that expression, that is in the case of a bar magnet, we are deriving an expression in the axial line as well as equatorial line for magnetic field, but it is deleted. So let me give you the expression for, in the case of a bar magnet, you will get an expression like this, that is B equal to mu naught by 4 pi into 2m by r cube. This is the expression that you are getting for a short bar magnet for axial point. Okay, like we have done electric dipole in the first chapter. Here we are doing for magnetic dipole. I told that bar magnet is an example for magnetic dipole, and for bar magnet we are finding magnetic field in the axial point and equatorial point. For axial point you will get an expression like this, but unfortunately this is deleted, so you just keep this expression in your mind. And here we want to prove that the solenoid will also behave like a bar magnet. That means if you are finding the expression for the magnetic field in the axial point of the solenoid, you will get the same expression as that of the bar magnet. Okay, here we are going to prove this. Understood? And you know this solenoid consists of large number of circular turns, isn't it? It consists of large number of circular turns, like if current is moving like this, okay, you can see large number of circular turns. So as a whole it will behave like a current carrying loop or a current carrying circular ring. And you have studied the expression for the magnetic field in a current carrying ring or a loop, like B is equal to, this is just a reminder for you, we have studied in the previous lesson, mu 0 I a squared by 2 into r square plus a square the whole raised to 3 by 2. Okay, if you have any doubt, you just check your previous videos. This is the expression for a current carrying loop, magnetic field in a current carrying loop. There we have studied two cases, for center as well as for an axis. Okay, so this expression you should be aware of. Now we will move to the proof that the solenoid also behaves like a bar magnet. Okay, for that we are considering a solenoid like this. Clear? Here, for this, we have considered a solenoid. Okay, you can see that I is the current passing through a solenoid. Now A, small letter A, is the radius of the solenoid. 2L is the length, total length of the solenoid. So this will be L, half length is L. Okay, and here we have considered n number of turns. N number of turns per unit length of the solenoid. Clear? And here, if you are moving a small compass needle in the neighborhood of a bar magnet and a current carrying solenoid, and if you note the deflections in the needle, it will be similar in both the cases. Understood? Now here, I am considering a point P on the axial line of the solenoid. And this P is at a distance R. Okay, R from the center at which the magnetic field is to be calculated. So from this, you know, this consists of large number of turns, and from this I have considered a small portion or a small element dx, and this dx is at a distance of x from the center O. This much clear? Once again, I is the current passing through the solenoid, A is the radius of the solenoid, 2L be the length of solenoid, N is the number of turns per unit length of a solenoid, P is at a point on the axial line, okay, which is to be calculated. That is what we are going to calculate. Then this P is at a distance of R from the center. Also we have considered a small element dx. It is a thickness dx which is at a distance of x from the center. So if total number of turns per unit length is n, what about the number of turns in this element? You can say, what is that? S. You can write the number of turns in the element dx is equal to, what is the value? It is small n into dx. Okay, small n into dx. Clear? Now you have seen that this is a circular element. So you have studied the magnetic field at a point due to the circular element, isn't it? So here we can write the expression. This is for a small element dx. So the magnetic field is dB, and dB must be equal to, as I told, the expression goes like mu naught I a squared. Okay, and for the small element the number of turns is n dx divided by 2 into, our general expression is r square plus a square the whole raised to 3 by 2. Clear? And here we want to find the expression for this dx element, isn't it? So instead of r, what will you write? Yes, it is r minus x. Okay, this distance r minus x the whole squared plus the radius squared the whole raised to 3 by 2. 2 into r minus x the whole squared plus a squared the whole raised to 3 by 2. Clear? Now here we are taking a condition where we are assuming that this P lies at a very large distance from O. So this value, that is the distance length, or that is the distance from O to P, is very much greater than the value A. Okay, so the condition is R very greater than A. In such a case, in the bottom part, what is the expression? Is if R is very much greater than A, this distance x, when you consider this distance also, I can say this R is very greater than x also. So the bottom part of this equation will turn to r minus x the whole squared plus a squared the whole raised to 3 by 2 will be equal to r cube, because these two terms will get neglected. Okay, so r square the whole raised to 3 by 2 will give you r cube. Clear? So the expression for dB will change to dB is equal to mu naught I a squared n dx divided by 2 r cube. Hope it is clear. Mu naught I a squared n dx by 2 r cube. Okay. So to find the total magnetic field at this point due to this current carrying solenoid, that is what we are finding, no? For that, what will you do? Yes, as usual, we will integrate the term. So by integrating, you will get B equal to all the constants taken outside, mu naught n I a square integral dx divided by 2 r cube. Okay. And when you integrate, you will give the limits, like if this is taken as an axis, okay, this portion will be L and this will be minus L. No doubt for that. So the integral limit will always be from minus L to plus L. Okay. So you can apply the limit, that is minus L to plus L. Clear for you? This is the range of variation of this value x. This can be from minus L to plus L. Now after integration, you will get the expression as mu naught n I a squared integral dx, and substituting the limit, you will get L minus minus L. Okay, that is the limit is like x into limit minus L to L. So this will be L minus minus L to L. Okay, divided by 2r cube. So the expression is mu naught n I a squared into 2L divided by 2r cube. Clear? And from this expression, you can rearrange it by multiplying it and dividing it by 4 pi. Okay, so please listen. Mu naught by 4 pi into these two, actually it will get cancelled, but the 4 pi that I am multiplying above in the numerator can be split into 2, so that I can write it as 2n, listen carefully, okay, 2n into 2l, then I, okay, then that pi, 4 pi, okay, a squared, just an arrangement only, then divided by r cube. Clear for you? That is 2 get actually cancelled, then multiplying and dividing by 4 pi. So here this is 4 pi given here. In the numerator there is 4 pi. I wrote it as 2, then 2 and pi. Okay. So from this expression, you can again rearrange, because you have studied the term magnetic moment. Do you remember that? What is magnetic moment? Yes, magnetic moment is given as NIA, NIA. Okay, that is number of turns into current into area of cross section. Clear? Number of turns into current into area of cross section. Now look here. Look this term carefully. What is this value? Here it is number of turns for the whole length. Okay, then the current is there, then pi a square will give you the area. Number of turns for the whole length, then current is there, area. Okay, so this expression can be changed to mu naught by 4 pi into 2m by r cube. Clear? 2m by r cube. So this is our final expression for the point on the axial line in a solenoid where we have calculated the magnetic field. So now you just have the reminder that I told in the starting that our expression for the bar magnet, the magnetic field in the axial point of a bar magnet is mu naught by 4 pi into 2m by r cube. So both are same. That means that the magnetic moment of a bar magnet is equal to magnetic moment of an equivalent solenoid that produces the same magnetic field. Also, in major cases, you can find close resemblance between this bar magnet and a solenoid. Okay, so study it well. It's a very important question. Bar magnet as an equivalent solenoid. Just to prove mathematically that the magnetic field at any point on the axis of a solenoid is equal to the magnetic field at any point on the axis of a bar magnet. Hope it is clear for you. So, note down the points. Note down all the points, okay? So that will be easy for you to study. Okay. Now we are moving to the next topic. So next topic, potential energy of a magnetic dipole in a uniform magnetic field. Okay, we have studied potential energy of an electric dipole in the first chapter. Same thing only. Here we are considering a bar magnet as a magnetic dipole. But before moving to potential energy, you should be clear with the torque on a magnetic dipole which is placed in a uniform magnetic field. That portion is also deleted by the CBSE in our revised syllabus. But without knowing torque, you can't come with the topic potential energy. So just I am mentioning torque here. For that, I have considered a uniform magnetic field, and in this uniform magnetic field, I have placed a bar magnet north-south, okay, NS. Its length is 2L. And you know the strength of the pole, each pole is M. In the last class we have studied that pole strength denoted by M. So for a electric dipole, you know the force on each charge because of the plus Q charge or because of the minus Q charge, there is a force which was given by the expression QE, isn't it? Q is the charge and E is the electric field. Then the force is given as plus QE or minus QE, it depends. Now in the case of poles, it is pole strength. So what will be the force acting here? You know this is north pole. So there is an attractive force towards the south, isn't it? So what about the force acting here? Yes, it is given by the pole strength M into the magnetic field. Understood? Similarly here it is south pole. So there will be a force acting in this direction which is given by MB again. Isn't it? So I can write here, this is the force acting MB here towards this direction because this is north and this is south, and here it is given like this, again MB towards the north direction. So force on north pole is MB along this direction, this is the direction of magnetic field. So along the direction of magnetic field, again force on south pole is MB, which is opposite to B. Okay, this much clear? So you can see that these are two equal forces and unlike forces. That means acting in opposite directions. So it form a couple, and this couple will tend to rotate the magnet, isn't it? So that is the torque acting on the bar magnet. So torque acting on the bar magnet is given by force into the perpendicular distance. So force, you know any one of the force because magnitude is same, MB. And the perpendicular distance is actually NA. NA is the perpendicular axis. You can see that this bar magnet is held at an angle theta with the direction of magnetic field. So you can find Na by taking the sine theta. Sine theta is Na by Ns, isn't it? Opposite side by hypotenuse. So I can write here sine theta equal to Na by Ns, or you want to find Na equal to Ns into sine theta, or 2L into sine theta. Ns is 2L, isn't it? So substitute the value in this expression. So you will get mb into 2L sine theta. mb into 2L sine theta, or you can write b into 2L m sine theta. What is this 2LM or m into 2L? What is m into 2L? Yes, it is capital M, which we call as the moment, isn't it? So you can write mb sine theta. mb sine theta. So this is the expression for torque on a magnetic dipole in a uniform magnetic field. So with this, actually this topic is deleted, but with this we are moving to the potential energy of a magnetic dipole. So always this torque tends to align the dipole in the direction of the field. So against this magnetic torque, you have to perform an external work, isn't it? So whatever work you are doing, in order to take this particular magnetic moment against the torque is stored as potential energy of the dipole. So a small amount of work done in rotating the dipole through this small angle theta can be taken as dW equal to tau into d theta, isn't it? Or mb sine theta d theta. So this torque will tends to align this particular magnet in the direction of magnetic field in this way. Okay. So if you want to take it back, you have to do an external work, and work is equal to tau into theta. You have studied this expression earlier. So instead of tau, mb sine theta d theta. Now this total work done can be calculated by integrating this expression. So W is equal to integral of dW. Okay. The limits is from theta 0 to theta. Okay. This is equal to integral of theta 0 to theta mb sine theta d theta. Clear? Now mb taken outside. So mb into integral of sine theta is minus cos theta, limits theta 0 to theta. So mb into minus mb into, clear, you can write cos theta minus cos theta naught. Okay. Now potential energy is actually this work done. So potential energy expressed by the letter U is equal to W, which is equal to minus mb into cos theta minus cos theta naught. Clear? Now let us assume this value theta naught is equal to 90 degree. Therefore, if theta naught equal to 90 degree, this term will get cancelled. Okay. So what is the final value? U is equal to minus mb into cos theta. Or in vector notation, you can express this as U is equal to minus m dot b. Clear? So here when theta equal to 90 degree, U equal to 0. That means when the first case, okay, when the dipole is perpendicular to magnetic field, what you can say is U equal to 0. And the dipole, the magnetic dipole means the bar magnet, when it is placed perpendicular to the magnetic field, potential energy is 0. And when theta is equal to 0, this is the case where theta equal to 90 degree. And when theta equal to 0, you can say that U is equal to minus mb cos 0, which is minus mb, isn't it? So what does it mean? When the magnetic dipole is aligned along the magnetic field, when theta equal to 0, magnetic field and the bar magnet are both parallel to each other, it is in the stable equilibrium. And it possesses minimum potential energy. Clear for you? And the third case is when theta is equal to 180 degree. The third case where theta equal to 180, when theta equal to 180, U equal to minus mb into cos 180, which is minus 1. So it will turn to plus mb. Okay. So this is the maximum potential energy, and it is the position of unstable equilibrium. That is, both are anti-parallel. That is, the magnetic field, the direction of magnetic field and the magnetic dipole are anti-parallel. It possesses the maximum potential energy, and it is the unstable equilibrium. Clear for you? So this is same as that of the potential energy in an electric dipole that you have studied in the first chapter. So go through this clearly. And that's all for today. Thank you.